What are we doing tonight?
We thought, Dave, we sent you over a couple of pages of more of these piecewise functions, and one of them, Patrick did the first page, and then the second page is blank. They didn't go through that in class.
Okay.
And what we thought we could do was maybe have you go over the first page quickly and sort of see if he got the work he did himself right. If he didn't, maybe show where he was wrong so we could try to get that corrected. And then, of course, on the next page, you want to work that through if we can, if we have enough time to handle that last problem.
Okay, sounds like a good plan. Let's let me pull these two files out on my desktop here. Let's see, I think, is this the first page or the second page? That's the second.
No, that'd be the second page, yeah.
Okay. Okay, let me have a look at this. So whenever x is less than 0, we have a function that has a, what kind of slope?
Negative.
What kind of slope did you draw there?
Positive.
Okay, so we need to switch that. And, in fact, it looks like you've kind of gone the opposite here. Let's go through this. Let me bring up my writing tablet.
You need your pad for this one.
In other words, when we go to graph this, start right there always. Top right corner. Okay? So we're first going to look at what our function is to the left of the y-axis when x is less than 0. That's everything over here. Okay?
Okay.
Well, the function says that it is f of x is equal to minus x plus 2. Well, if I gave you that to graph, how would you graph that?
You'd start at the
Start at 2.
yeah, start 2.
And what's the slope?
It's negative 1.
And how do I get my second point then?
You'd go over 1 to the left and then up 1 to the right, left.
Yeah. In other words, if I go up 1 and left 1, that gives me a negative slope. That's what I want. And I stop it right there. The closed 0 or an open 0 go here?
Open.
Open for the moment. May turn into closed depending on what the rest of the function looks like. Okay? Now, look down here. In other words, now we're looking at whenever x is positive or equal to 0. So now we're going to graph everything to the right of the y-axis. Well, f of x is equal to x. Where does that begin and what is that slope?
It starts at 0 and has a slope of positive 1.
And is it a closed dot at 0?
It's a, yeah, closed line.
Okay, and how do I get the rest, another point on that line?
You could go up 1 and over 1 to the right.
Right there. And it stops right there. Arrow there, arrow here. Okay? And notice what you did. This was kind of correct. It just looks like you got it reversed a little bit. And then the first one you've got has a y-intercept of 2, but you got it going to the wrong way. In other words, if you take this, make it go that way, and take this, make it go that way, then you would have had it right. Okay? So you're not that far off. You're not as far off as it looks from the picture. Now, let's talk about each of these here. We have to do these for each problem, right? Yeah. So, the domain. Okay, if we look at my graph, we can see that the x goes from negative infinity to positive infinity, which is what you wrote. That's good. Where is the thing increasing and where is it decreasing?
Hold on. It's increasing between the x if x is greater or equal to 0, and it's decreasing to the x is less than 0.
Yeah, and if I had to put that, have you learned interval notation? Is that what this is?
Yeah,
Or just defining it by this? Okay. So you've said it's increasing whenever x is greater than 0, which is this part, and it's decreasing when x is less than 0, which is that part. Okay? Find f of 0. Well, when x is 0, which piecewise function are we using?
You're using the second one?
Yeah. So what is f of 0?
If x is
Plug in x for 0. What is f of x?
oh, all right, sorry.
So f of 0 is what?
It's 0.
Uh-huh. And what's f of minus 3? Which piecewise function are we going to use?
Oh, we use the top one.
Okay. Plug in minus 3 for x. What do you get for an answer?
-1.
Be careful. It's minus x plus 2. And we're going to plug in a minus 3 for x. What's a minus 3 plus 2?
Minus 3 plus 2.
That turns into a plus 3. Because you basically have, what this really means is minus 1 times minus 3. Okay, so minus times minus is plus. And so you have 3 plus 2 or 5. So f of minus 3 is equal to 5. And we can kind of see that. If we go over to minus 3 on the x-axis, we're way up here. 5 looks about right. All right, let's look at the second one. Now, when you see a piecewise function that has just a number for part of it, what does that translate to in terms of appearance? If I told you to graph just this, what would that look like?
It'd start at -y. It'd start at -1y.
Is it a horizontal line? Is it a line that has slope? Is it a vertical line?
It's a horizontal line.
Yeah, exactly. So if I were to graph that whole thing, it would be that right there, that horizontal line at -1. But I'm not going to graph it the whole way. I'm going to look first at my domain. Well, the domain says it's only -1 when x is less than 1. So let's go to 1. So here's -1 on the y-axis. So what's this going to look like? It's a horizontal line that stops where?
At 1.
Closed dot or open dot?
Yeah, closed.
Less than 1 only. Whenever you see a less than or a greater than, that's open dot. To get a closed dot, it's got to be less than or equal to or greater than or equal to. Okay?
All right.
Now, to the right of 1, it's this function over here. So where do I start? Because that function is not going to intersect the y-axis. So I could pretend it intersected the y-axis and then erase it, but that's not really a good way to do it. To figure out where we start here, plug in 1 for x. What do you get?
You get 2.
Plug in 1 for the x in the bottom. Get 2 minus 2, 0.
Oh, all right.
That means that this thing starts right there. When x is equal to 1, y is equal to 0. And it's a closed dot because it's whenever x is greater than or equal to 1. Now let's finish this graph. I've only got the first point on it. How can I get another point?
You could go up to over one to the right.
Right about there. Connect the two dots. There's your graph. What's the domain? Looks like you got the domain correct. Where's the function increasing? You got that right. When x is greater than 1. Actually greater than or equal to 1, I think is what that says. Is it decreasing when x is less than 1?
No.
No, it's not decreasing anywhere. There's nowhere on this piecewise function that the function decreases. So that would be never. Now find f of 3. And always figure out, whenever you're evaluating the function, figure out first which one you're going to use. So f of 3 is which one?
It would be the top.
Hold on. The top one is whenever x is less than 1. The bottom one is whenever x is greater than or equal to 1. So f of 3 is which function?
The bottom one.
Okay. Plug in 3 for x. What do you get?
Plug in 3 for x.
Into the bottom one?
I can get 4.
Okay. That's what f of 3 is 4. Okay. Now f of minus 1, what is that equal to? What is y, or f of x, when x is minus 1, right there?
It would be 0.
Read the y value off of my graph. Here's the x value, minus 1. What's the y value? Here's the y value right here.
It would be negative 2.
What's that line there? What's that horizontal line on the y-axis? It's at minus 1, right?
Yeah.
So f of minus 1 is equal to minus 1. But that's a bad one to give you, because what is f of minus 5 equal to?
Minus 5.
No, see, that's why this was a bad question. Because you come away from this question thinking that the answer is whatever's inside here. And it's not. Go to minus 5 on the x-axis. What is y equal to it when x is minus 5?
Negative 1.
Exactly. Okay? You got it now?
Yeah.
Okay. Let's go to 3. Okay, now they give you the piecewise equation, and they want you to come up with it. Notice that this horizontal line better be y equals a number, or f of x equals some number. 2. Okay? But we want to start from the left, which that's fine. In other words, I always said start from the left, so we're going to look to the left of x. What's going on? Well, is this a positive or a negative slope?
It's a positive.
Okay, so should this be a positive or a negative number right there?
Be positive.
Again, yeah, excuse me. Sorry, I did this wrong here. Let's back up a second. Okay, we're going to start from the left. Okay? So this line right here, can you see me pointing that out?
Yeah.
That is this function that goes right here. Because we're to the left of 0. So it's got to be this function. It doesn't have anything to do with that function. It's strictly this function here. What's the equation of that line right there? That's what's going to go in my f of x, is the equation of that line right here. Whenever x is less than 0, we're going to have this line here. Well, to figure out the equation of that line, what's its slope?
Hold on.
What is the slope?
It's the rise or run I'm trying to figure out.
Yeah. No, it's what it appears to be. It is a little hard to figure out. The way to figure these out is to find a point on the curve that is on an intersection of the grid, like there, and find another point. Well, there's another point that's on the intersection. So figure out the slope between this point and that point. So how much do you have to go up and how much do you have to go over?
Sorry, my eyesight's terrible. You have to go up 3 and over 3?
Yeah. So what's the slope on this line?
1.
Okay. So the equation of that line then is going to be x, but what's the y-intercept?
It's at 0.
Is it? The y-intercept? In other words, look at just this line right here. Where does it touch the y-axis?
Oh, sorry, 1.
Okay, so that's the equation of that line right there. That takes care of everything to the left of the y-axis. And that's where we want to start. You kind of got it reversed here. That's not the right equation anyway, but you need an equation up here that has an x variable in it because we've got slope. This, what you've put there, is the equation of this line right here, but it's only when x is greater than 0. So 2 is right for the next part. And it's when x is greater than or equal to 0 that f of x is equal to 2. Okay, you see that?
Yeah.
Okay. Domain, you got right. Increasing. Where is this whole thing increasing?
It's increasing at the sorry. If x is greater than 0, I mean less than 0.
Less than 0. Wherever x is less than 0, this function is increasing. Even if I go out to x is minus 1,000,000, it's way down here, but it's increasing. It's increasing all the way from negative infinity to 0. And I call that 0 because when I'm defining where it's increasing or decreasing, I'm going to define it in terms of x, not y. Not f of x, but x. In other words, wherever x is less than 0, this function is increasing. But decreasing.
When x is greater than or equal to 0?
Okay, you see anywhere on that where it's decreasing?
No, so it's never decreasing.
Never. That's all there is to increasing and decreasing, is looking at the graph and figuring out where it's increasing or where it's decreasing. Well, when it's horizontal, it's doing neither. So this one is never increasing. Okay, what is f of 0? First of all, which function are we going to use when we evaluate f of 0?
If x is greater than or equal to 0.
Okay, so what's the answer to f of 0?
It's 1.
What is it? Read it off of there. What is it right there?
0.
No. When they say f of 0, they want the y value. They want the f of x value, not the x value. They want the f of x value.
Alright, so we are 2.
Yeah. So f of 0 is not here. That's the wrong function. That applies only when x is less than 0, not when it's equal to 0. When x is equal to 0, we're right here. So f of 0 would be 2. What is f of 4?
Yeah, if x is greater than 0?
No, what is f of 4? Evaluate this thing for f of 4.
It'd still be 2.
Exactly. What's f of 8?
Still 2.
What's f of minus 3?
Just hold on real quick.
Okay. Go to the minus 3 on the x-axis. Go down and find the y value. What's that y value right there?
Negative 2.
Uh-huh.
You see what I'm trying to do? Yeah.
Okay.
It's a little-
Let's do this in pieces, starting from the left. Now, one of the problems is you starting from the right. In other words, when you do x greater than 2, you're doing this part first. There's nothing wrong with that. Sometimes they'll even give them to you like that. But it's just not the same order. In other words, if you always use the same methodology, you won't be inclined to forget it. And the methodology I like to use on piecewise functions is always start from negative infinity on the x-axis. Okay, so if I'm going to define this function as a piecewise function, I want to start right here with x. What is my x going to be? So if I want to go from the left, what is x everywhere here?
Everywhere on that line.
Well, how is the domain defined for that part of the piecewise function? That's what this is over here, is defining the domain for each part.
Oh, alright, so it's 0.
It's less than 0. In other words, we're going to start by describing our function wherever x is less than 0, because I can see that that's that whole thing. This piece is when x is less than 0. You see that?
Yep.
Okay. What's the slope on that line?
It's 1.
Plus or minus?
Minus 1.
Okay, that means y is equal to minus x plus b. What's its y-intercept? This line right here, what's its y-intercept?
Negative 1.
Uh-huh. There's the equation of that piece of it. It's got a slope of negative 1, and it hits the y-axis at minus 1. Okay? Now let's go to the next piece in order. I'm not going to jump to this. That would look strange over here. So what is the domain of that part right there?
2.
When I say domain, what is its beginning x value? What's its ending x value?
Alright, so it's 2 and 0.
Uh-huh. So x has to be greater than or equal to 0, because I see a closed dot right there. And it has to be less than 2 with an open. In other words, it's less than 2 because there's an open dot right there. What's the equation of this middle piece? What's the equation of that line? fx is equal to what?
Wouldn't it just be negative 1?
Positive 1.
Oh, yeah, sorry.
It's a horizontal line. All horizontal lines are y equals some number. Okay, now what's the rest of the domain? What do I need to put over here? What's this part right here?
Alright,
X is what?
2.
No? It starts there.
Oh, yeah, x is greater than 2.
Greater than or equal. You see why it's greater than or equal?
Yep.
Closed dot right there. Okay? So now we need the equation of that line. Well, let's come up with the slope first. What's the slope of that line?
Mm-hmm. Be 3 over 1.
You know, it looks like 2 Looks to me like I got to go up 1 and over 2.
Oh, guys.
Or let's see, if I went up 1, 2, 3, and then I'd have to go over 1, 2, 3, 4, 5, 6. So that's a slope of 1/2. Okay, so the first part of that function is there, right there, 1/2 x. Well, I can see that if that were to continue over, it would intersect right there. So I know the rest of it's plus 1. Is there a way to get that plus 1 without drawing an invisible line over to connect with the y-axis? Yeah, there is. And here's how we would do it. I know it's 1/2 x plus b, right? The equation of this line. Okay. And I know that when x is 2, y is 2. So there's the equation of that line. Now I can plug in the one known point that I know is on that line, 2, 2. So I'm going to plug in 2 for y. I'm going to plug in 2 for x. And that allows me to calculate b. b equals 1. Now I can go back in and fill in that 1 right there. This is a better method right here than extending that line over to the y-axis. Because for one thing, it won't always go over and come out at a nice whole number. And you need to be able to figure it out algebraically. And this is the way to do it. In other words, we know this much of the equation merely from looking at slope.
Hold on for a second. We got his glasses screwed up.
Okay?
Sorry.
It's all right.
Okay, there you go. All right. So go back to that. Can you go back to that part about solving the equation just so we can make sure you got it?
Yeah. So we know that this equation is 1/2 x plus some b, right? And let's say that we couldn't read the graph well enough to figure out where that would intersect the y-axis if I were to extend it all the way over. If I knew for sure that that crossed right there, then I'd just go ahead and put plus 1. But I don't know for sure. So I got to figure out what b is. Well, I can figure out what b is by pulling any point off this line, plugging it in for y and x. I pulled this point right there, where x is 2 and y is 2. I could have just as easily used that point. Let's use this point. X is 8, y is 5. So I'm going to plug in 8 for y. Excuse me. X is 8, y is 5. So I'm going to plug in 5 for y, 8 for x, and solve for b. That also gives me b equals 1. So now I know what b is. I can go back and replace it. And there's the equation of that line right here. That is the equation of that line. It only applies when x is greater than or equal to 2. So there's my answer. 3 different functions. What's the domain?
It's in, for the first one it's infinity, positive infinity.
Okay, start your domain from negative infinity. And we're talking about the x-axis only. So what are the allowable values for x? Are there any values for x that I can't plug in? In other words, does this cover all real numbers? Or are there some numbers that you can't plug in for x?
No.
All real numbers then. In other words, this goes from negative infinity to positive infinity, with all values in between. And if I look at the graph, I can see that there are no values of x that I can't plug in. That there's no vertical asymptotes or anything. Okay, so all reals for domain. Where's the function increasing?
The function's increasing at the x is...
Where in the domain is it increasing? It's never increasing at a point. It's always increasing over an interval. So what is the interval that the function is increasing? And they may not have given this to you like this in class, so let me just tell you. The function is increasing over this interval right here. From 2 to infinity. On the x-axis, f of x is always increasing. You see that?
Yep.
I could also write that as x greater than or equal to 2 is where it's increasing. Usually when you talk about increasing and decreasing, they like the answers in interval notation like that. But I don't know, your class, whether this is acceptable or what. Both of these say the same thing. Where is it decreasing?
It's never decreasing.
About here. In other words, know what decreasing means. Decreasing means it goes from upper left to lower right. A function that has a negative slope is always decreasing. You see why that's decreasing?
Mm-hmm.
In other words, starting from the left, way out here, no matter where I go on that line, the next point going to the right is lower, 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 all the way to there. So this function is decreasing whenever x is less than 0, or if I wanted to write it in interval notation, it's from minus infinity to 0. That's where it's decreasing, on that interval. Okay. F of 2. Which function are we going to use to evaluate f of 2?
Which one?
Top, middle, or bottom?
Bottom.
Okay, what is f of 2?
Okay.
It's 1/2. I'm going to plug in 2 for x. Okay, sorry. I thought you gave me the wrong answer at first. My mistake. What is f of 1? Yeah, f of 2, you're correct. That is 2. What's f of 1, and which function am I going to use?
Are you going to use the middle one?
So what's f of 2?
1.
Correct. All right. Should we go to the next page? That's everything on that page, I believe?
Yep. That's it, David. Yep.
Okay. Okay, this word problem here. The cost to send a package between 2 cities is $8 for any weight less than a pound, and it increases by $4 when the weight reaches 1 pound, and again each time the weight reaches a whole number of pounds after that. Well, this has the appearance of a piecewise function, correct?
Mm-hmm.
Okay, so let's make a function. Cost of W, with W being the weight. What goes here?
All done. I'm just drawing that equation. Alright, so what we do there is 3, 4.
Start.
4.
Okay, first of all, we're going to end up with a graph where W is the horizontal axis and C of W is the vertical axis. Okay, So first of all, can W be negative?
No.
No, it can't. It can only be 0. Can't ever be negative. So the first thing I know is I'm not going to have any x's that are negative. But x can be less than a pound and greater than 0. In fact, yeah, what would the cost be if it was x was anything less than a pound?
It'd be $8.
Aha. That's where that goes right there, is 8. So my cost is 8 as long as W, not x, is between 0 and 1. Well, the next interval is going to be what? In my domain. If my first interval was from 0 to 1, what's my next interval?
You could do 1 to 2.
Well, or greater than or equal to 1. That covers all weights. Notice that these two domains go from 0 to infinity. Okay? What is the equation going to be when it's greater than 1? The cost increases by $4 per pound. That's the slope, 4.
So it would be 8 plus 4.
Well, it would be 4x for starters. Now let's see if that's enough. Well, if W was 2, what would the cost be? According to what I've written.
You got $12.
Well, no, according to what I've written, if W is 2, the cost would be 8. It would be 4 times W. Excuse me, I keep writing X. I mean to write W there. So that's not enough function. We need more, because we know the cost is not going to be $8 for 2 pounds. It's $8 for 1 pound. So what do they mean here? The cost increases by $4 per pound when it reaches 1, but it started with 8, so must be that. In other words, now when the weight is 1, the cost is 12. Well, that makes sense. It's $8 up until 1 pound weight, but the moment it hits 1 pound, you add another $4 to that thing. Well, when W is 2, we're going to add $8 to 8. So this function perfectly reflects the words. Not quite, it doesn't. Yeah, not quite. In other words, the words say that each time the weight reaches a whole number of pounds after that, you're going to add another $4. Well, that's not what this says over here. This says that I've drawn says that when W is 1.5, my cost is going to be 1.5 times 4, which would be 6 plus 8, $14. But that's not what that says. That says you're not going to add another $4 until you reach 2 pounds. So you were actually right on the domain here. This domain is from 1 to 2 pounds. Like that. And does that work? Let's see. We should be paying no, hold on. The cost between 1 and 2 pounds is 12, right?
I'm sorry, why?
Well, because you pay $8 for anything up to a pound, and you pay $4 per pound for every integer number of pounds.
He didn't hear the question, David. I actually interrupted you a little bit. He didn't hear the question that you asked him. So
Yeah. I'm trying to wrap my hand around this because I hate this question, but no, I'm quite certain that this is going to be the answer. Notice what I'm doing here. Does this make sense? In other words, when the weight is between 0 and 1 pound, the cost is $8. When the weight is between 1 and 2 pounds, the cost is $12. In other words, 1.5 pounds, it's $12. It's not based on that original function I wrote in there.
But is that so? Is 1.5 a whole number?
Well,
or does it have to go to 2 pounds?
Yeah, 1.5 is here, but the cost is $12 according to this. The cost increases by $4 when the weight reaches 1 pound. Well, if you increase 8 by 4, you get to 12.
Right.
And then it goes up another 4 when you reach the next whole number of pounds after that. So the way I've written it here is correct. Now let's, not quite sure how to continue to write it. In other words, it goes on forever, like this. That's why I hate this problem. But the net result, when I go to graph it, is a step function. Here's 8. Here's 1. Here's 2. Here's 3. Here's 4. In fact, this is a very good real-life model of a step function. The postal cost of mailing an envelope. Follow me here. These are all horizontal lines. Now, you see why this makes sense?
Yep.
And why they should all be horizontal lines. No slope lines. There is no slope anywhere in this piecewise function. In other words, when the weight is between 0 and 1, the cost is $8, no matter whether it's 0.1 or 0.9. When the weight is from 1 to 2, up to 2, cost is $12. Doesn't matter if it's 1.5, 1 1/4, 1 3/4. Cost is still $12. The moment we reach 2 pounds, we go up by another $4. It said add $4 every pound. Okay? So this fits this perfectly, including the greater than or equals, equaling closed dots. But how we write the whole thing, I'm not sure. You could use a greatest integer function, but I don't know if that's what they want you to use here or not. In other words, the reason I don't like this problem is because there's an infinite domain. We could keep writing. It asks you to complete the table, graph the function. Well, we've already graphed the function. Let's go ahead and complete that table based on our function. What's the cost for when the weight's half a pound?
Would it be $8?
$8, right? Let me bring my function in here. What's the cost when the weight is 1 pound?
$8.
What's the cost when it's 1.5 pound?
10.
Goes up by 4.
Well, it doesn't only go up by 4 every
pound.
So
Every pound. So 1.5 falls right there.
What he was saying, David, is that he thought that 1.5 would be just a half of the $4. But what the function says is that once you break that pound and get into the next function. It's $4 no matter what. You don't get any fraction discount.
That's the way I interpret that. The cost increases by $4 when the weight reaches 1 pound, and again each time the weight reaches a whole number of pounds after that. So 1.5 would just be an extra $4, so the cost would be 12. And that's what my graph shows. If you go to 1.5 on the W-axis, well, you're at 12. Anywhere between 1 and 2, the cost is $12. How about at $2? $2, you got an open circle and a closed circle. Which value are we going to use for our cost?
16.
Yes. In other words, we use this one here. Because when W is 2, you're not down here in the open circle, you're up here when it's precisely 2. And that's what the word problem says, is that when we reach the next whole number, which would be 2, we go up by another $4. So at 2, the cost is going to be 16. How about 2.5?
It'd be about 20.
2.5, right there. What's the Y value at 2.5?
20.
Look on my page. What's this Y value?
16. Oh,
Okay.
no, I see.
Okay. In other words, this is a step function. This is the exact same thing as a step function. There's another model that fits this perfectly, and that is the age of a kid on the x-axis and the grade level they're in. In other words, if a kid is from 6 to 7 years old, they're in the first grade, right? No matter whether they're 6.5, 6 3/4, or barely 6, they're in the first grade. But from 7 to 8 years old, they're in the second grade. You see how these two compare? They're both step functions. And they're real-life models of how a step function is supposed to function, how it's supposed to act.
Hey, David?
Yeah.
You know, just trying to track this, we originally had, when he had 1 pound, going back to the fill in the blanks here, when we reached 1 pound, we had $8. It was half a pound, $8, 1 pound, $8.
Well,
Then
except the word says that less than a pound is $8.
Right, that's what I said. Half a pound is $8. 1 pound is $8.
No, 1 pound's not $8.
Okay, that's where he has his error on here.
When you get to 1 pound, you have to add that extra $4. If you would have gone into this post office and it would have weighed exactly a pound, they're not going to charge you $8 because they're going to charge you $8 for anything less than a pound.
Right. Okay.
The moment it hits 1 pound, it goes up by $4.
It's $12.
Yeah. So that original picture I had was correct, that it goes 8, 12, 16, and 20.
Right. Okay. So you got this one here is where we have to change this thing, because when you get to 1, you're 12. So this is 16, 20. You know, we're still screwed up here, David. We've got 1 pound at $12 now because he's added his $4.
Right.
Then
Look at my chart. Look at my chart. Notice that when we got to 1 pound, we're here, not down there.
Right. And when he's at 1.5 pound, he's still at $12.
Right.
Okay. Then when he hits the next one, then it would be 16 to 2 pounds.
Right.
And then that would be $16 for the extra half pound for 2.5 pounds.
Exactly.
All right, then he's got it. He had it right. He just had that first one where it reached 1 pound. He had it at 8, so he threw the whole graph off.
Right. Right. Yeah. This is a classical step function where the closed dot is on the left. And this step function matches ages and grade levels also.
Sure.
If you're exactly 6 years old on September 1st, you get into the first grade. But if you are 6 years and 364 days old, you still are in the first grade. In other words, you don't go into grade 1.5 when you get to be 6.5 years old. You stay in grade 1 the whole year until the next year, in which case you're 7 years old. Now you go into grade 2. The whole year that you are 7.
Okay, well that's good then, David. I think that's probably good for you tonight.
Yeah, and we graphed it, just the step function, just like I graphed there.
All right, David, thanks.
You're welcome. I'll talk to you guys next time.
Yep, talk to you later.
All right.
No, put down here, Pat.